So now we're going to do the exact same problem, but turbulent. Okay, we have the same settings, but now we're assuming that it's turbulent. We want to find what is the total drag for 100 meters per second and for 1,000 meters per second. What is it? What is it? Okay, so this is really easy, honestly. We don't have to do all that much here. Reason? Because we don't have all that much we can do because there's no particular models for this. And so all we have to go on is simply that our skin friction coefficient when we're turbulent is equal to 0.074 over the Reynolds number based on the chord to the fifth. Okay, so that is it. We already know what our Reynolds number are because our Reynolds number in this case is going to be equal to 1.36 times 10 to the 7th. And our Reynolds number in this case is equal to 1.36 times 10 to the 8th. And so we can just plug those in and we have it. And this is a 5. There you go, 5. So we'll get our skin friction coefficient, then our drag in the first case and the second case. Okay, so we have 0.074 all over 1.36 times 10 to the 7th to the 5th power, to the 1/5 power, goodness. Gotta be careful. And so this would be equal to 2.77 times 10 to the -3rd. Then we plug that into our drag equation, just like last time. I'll rewrite the equation, but I won't plug the numbers in. I'll just show you what the answer is. So that's going to be 1/2 rho infinity times v infinity squared times s times my skin friction coefficient. And it's going to be equal to 675.9 newtons. And the total drag then is equal to that times 2, because we have to do both sides of the flat plate. And it's going to be equal to 1,352 newtons. Okay, so now let's compare to our earlier case. So if we want to look at the ratio here, so my drag in the turbulent case over my drag laminar, well, it's going to be equal to 1,352 in the turbulent case, all over 175.6 in the laminar case. So that's a set factor of 7.7. So if I'm turbulent versus laminar, I have nearly 8 times the drag when I'm even going incompressible speeds. So there's a reason we want our flow to be laminar if we can, okay? Because we're going to greatly increase our friction. But now let's check that at the 1,000 meter per second case. Still turbulent, but 1,000 meters per second. Okay. So everything else is pretty much the same. We first calculate our skin friction coefficient. That's going to be equal to 0.074 over, not the square root, goodness, a Reynolds number based on the chord to the 5th power, 1/5 power. Be careful I say these things. And that comes out to be 1.34 times 10 to the -3rd. And so my drag force, calculated based on that, is simply going to be equal to 32,700 newtons And my total drag will be that times 2. $65,400 newtons. So if we compare one more time, we'll see that when we go to even faster speeds, the drag turbulent over drag laminar would be equal to 65,400 newtons over 5,026 newtons, which is equal to a factor of 13. So what you're seeing here is that as I go to higher speeds, there is a greater and greater penalty for being turbulent versus laminar, okay? And it's still a big deal even when I'm moving at, a Mach number 0.3. I'm still having significantly more drag when I'm going turbulent versus when I'm going laminar. So we need to, as much as we can, minimize turbulence. Try to keep our flow laminar and to avoid this. Cool, there we go.